All right, we're going to now redefine the trigonometric functions in terms of the angles and sides in a triangle. And if you've seen trigonometry before, like in high school, you probably saw this context. So let's let A be an acute angle in a right triangle. First of all, the long side of a right triangle, which is opposite the 90-degree angle, is called the hypotenuse. The other two sides are labeled relative to angle A. So the side that's next to angle A is called the adjacent side, and the side opposite angle A is called the opposite side. Okay, notice that had A been chosen as the other acute angle in the triangle, that the naming of opposite and adjacent would be exchanged from where they were a moment ago. So we'd have the adjacent side here next to the angle A, and the opposite side opposite the angle A. Okay, so the trigonometric functions are defined as follows. Sine of the angle A is the opposite side divided by the hypotenuse. Cosine of A is the adjacent side divided by the hypotenuse. And tangent of A is the opposite side divided by the adjacent side. And the other three trigonometric functions are defined as would be expected from the reciprocals. So cosecant would be hypotenuse divided by opposite. Secant of A would be hypotenuse divided by adjacent. And cotangent of A would be adjacent divided by opposite. Okay, and with this comes a world-famous trigonometric mnemonic. SOHCAHTOA. SOHCAHTOA reads as sine, the C is cosine, and the T is tangent, and it basically reads as sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. All right, let's see how to use these definitions. Okay, so here we're given a triangle, and we're asked to read off of the triangle a few different trig values of angle A and angle B. So before we can do that, we are missing one side length of this triangle, so we should figure that out. Let's call this side here little a, and the first thing we should do is find little a, and of course we'll use the Pythagorean theorem.
Sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, joy! Rapture! I've got a brain!
We know that a squared plus 77 squared is equal to 85 squared, the hypotenuse. So a squared is 85 squared minus 77 squared. So using a calculator, you can get that a squared is 1,296, and therefore a is the square root of that, which is 36. Okay, now that we have all three sides of our triangle known, we can evaluate these trigonometric function values. So sine of A. All right, well, let's remember SOHCAHTOA. So sine is opposite over hypotenuse. So for angle A, the opposite side is 36, and the hypotenuse is 85. So sine of A is 36 over 85. What about cosine of A? Well, SOHCAHTOA, cosine, CAH, CAH. Cosine is adjacent over hypotenuse. So in our triangle, adjacent is 77, hypotenuse is 85. And tangent of A, TOA, tangent is opposite over adjacent. So opposite angle A is 36, adjacent to angle A is 77. All right, very good. Let's find the sine and cosine and tangent for angle B. So sine of B is sine opposite over hypotenuse. But for angle B, the opposite side is now 77. So this will be 77 over hypotenuse of 85. Cosine of B is adjacent over hypotenuse. So adjacent to angle B is 36. Hypotenuse is 85. And tangent of B, TOA, TOA, opposite over adjacent. So for angle B, the opposite side is 77. And the adjacent side is 36. And there we are. I want to point out a quick pattern here that's rather nice. And that is, if you'll notice, the sine of A is equal to the cosine of B. And the cosine of A is equal to the sine of B. It is true that the sine of an angle is the cosine of its complement. And that's a property called a cofunction identity. And we're going to work with it much later in this course. Okay, we encountered this exact example in our last lecture. And it took us quite a bit of analysis to work it out using identities. But I'd like to show you a different way of working it out by taking advantage of this new SOHCAHTOA concept that we've just uncovered. So what do we have here? Well, we're told that cotangent of an angle theta is -5/7. So let's draw a triangle and put theta on that triangle. Okay, so what we're going to do is we're going to place a 5 and a 7 on this triangle using the fact that we know cotangent of theta is -5/7. Now, cotangent's not part of the SOHCAHTOA mnemonic, only sine, cosine, and tangent are. So the first thing we should do is actually write this in terms of tangent. So cotangent of theta is -5/7. Therefore, tangent of theta, which is the reciprocal, would be -7/5. Tangent is the opposite over the adjacent. So looking at our triangle, we can label this side here as 7 and this side here as 5. Now the problem is that tangent of the theta in this triangle is actually +7/5, but tangent of the theta that's in the problem that we're really interested in is -7/5. So to rectify that, I'm going to just put a little apostrophe here next to our theta, which tells anybody reading this problem that this isn't quite the exact same theta, but it's related to it. Okay, so now we're going to use the Pythagorean theorem to find the hypotenuse. Let's call the hypotenuse C. So we know C squared is 5 squared plus 7 squared. So that would be 25 plus 49. So C squared is 74. And therefore C is the square root of 74. And if you remember the example from last time, square root of 74 certainly featured prominently in our answer. Okay, so we're after the 6 trigonometric functions. So that would be sine of theta, cosine of theta, tangent of theta, etc. Now, we can read these directly off our triangle, but we have to be careful because our triangle only has positive values on it. So what we need to do is pay attention to the quadrant of our original theta. And we did this last time. We saw that cotangent of theta is negative, and theta is between 0 and 180. And we use that to deduce that theta had to be in the second quadrant. So that means that cosine, tangent, secant, and cotangent will all be negative. And once we've determined which ones are positive and which ones are negative, now we can read everything off the triangle. So sine of theta will be opposite over hypotenuse, right? That's SOH from SOHCAHTOA. So that would be 7 over rad 74, which we can rationalize. Cosine of theta will be adjacent over hypotenuse, which also rationalizes. Tangent of theta will be opposite over adjacent, so that's 7 over 5. Cosecant of theta will be the reciprocal of sine, and sine is opposite over hypotenuse, so cosecant will be hypotenuse over opposite. Secant of theta is the reciprocal of cosine. Cosine's adjacent over hypotenuse, so secant will be hypotenuse over adjacent. And cotangent of theta will be adjacent over opposite. So with very little writing, we were able to get exactly the same answer that we obtained earlier. And our earlier work certainly took a lot of writing. So this is definitely a faster way of working out these particular values. It does come with the burden of managing these negatives because the triangle only has positive side lengths. So as long as you're taking care of the negatives according to the quadrant of theta, then you should have no issue with this. And I do encourage this technique. We are now going to look at two very special right triangles. So the first one is the 45 degree, 45 degree, 90 triangle. And the other one is the 30, 60, 90 triangle. And when you draw the 30, 60, make sure the 30 goes in the narrow angle slot and the 60 goes in the larger angle slot, of course. So using SOHCAHTOA and some basic geometry, we can actually figure out what the side lengths are on these triangles and therefore deduce things like the sine, cosine, tangent of 45 degrees, 30 degrees, 60 degrees, any of the angles on these triangles. All right, so let's start by playing around with the 45, 45, 90. So let's decide that this base length is 1, and since this is a 45, 45, 90 triangle, this altitude over here, this other side, is congruent to the base, so it's also a length of 1. And let's just call this side C, and we'll use the Pythagorean theorem to determine the value of C. So C squared is 1 squared plus 1 squared. So C squared is equal to 2, and therefore C is equal to the square root of 2. Okay, so returning to our 45, 45, 90, we actually know the ratios of these sides are 1, 1, and root 2, which means you could read trig function values off of this triangle, like tangent of 45 degrees, opposite over adjacent. That would be 1, and indeed tangent of 45 degrees is 1. All right, let's look at the 30, 60, 90 and do something similar to it. So let's decree that the small base here is 1, and this time this is not an isosceles triangle, which means we don't know any of the other side lengths. So we're going to perform a little move where we create a second one of these triangles and place it adjacent to the first one. So we have another 60-degree angle here and a 30-degree angle here. But the 30 plus the 30 makes 60, so we have a 60, 60, 60 triangle, which is equilateral, which means we know all three side lengths are congruent. All right, well, this particular side length right here is 1. So that means this part is 1. So the entire side length is 2. And that means this is 2 and this is 2. So the only thing missing is the altitude of the triangle. But again, we can use the Pythagorean theorem and say, well, a squared plus 1 squared is equal to 2 squared, and solve for a. So a squared is 2 squared is 4, minus 1 squared, which is 1, so a squared is equal to 3, and therefore a is the square root of 3. So returning to this triangle here, if the small side has a length of 1, then we know the medium side has radical 3 and the long side has a length of 2. So this triangle is often called like a 1, 1, root 2 triangle, and this triangle is often called a 1, root 3, 2 triangle. And now we can again read sine, cosine, tangent of any of those angles at this point. All right, so let's work these out. And we're going to use one of the triangles, obviously the 30, 60, 90 triangle that we just found. And on your homework, you have a number of these to work out. And I very much strongly recommend that you do not just reach for a calculator to get these answers. And you don't just look them up on a table, but you learn to draw the triangles yourself. Doesn't take very long to learn them. And once you know them, then you'll be able to conjure up all of these trigonometric function values whenever you need them. So you do need to know these to be a functional citizen in the universe of mathematics. All right, so let's draw the 30, 60, 90 triangle. So we'll place the 60 here and the 30 in the narrow slot. And we know the side lengths are 1, root 3, and 2. Okay, so all of these are asking about 30 degrees. All right, sine of 30 degrees. Well, sine is opposite over hypotenuse, so that would be 1 over 2. Cosine of 30 degrees, well, that's adjacent over hypotenuse, so that would be rad 3 over 2. Tangent of 30 degrees, that's opposite over adjacent, so we could write 1 over rad 3, except that rationalizes, right? 1 over rad 3 times rad 3 over rad 3 comes out to rad 3 over 3. And that's a better way of writing that. We should rationalize when we can. All right, cosecant of 30 degrees. Well, sine is opposite over hypotenuse, so cosecant would be hypotenuse over opposite. So that would be 2 over 1, and we'll just write that as 2, of course. Anything over 1 is just the thing. Secant of 30 degrees. Well, reciprocal of cosine. Cosine's adjacent over hypotenuse, so secant will be hypotenuse over adjacent. So that's 2 over rad 3. But we'll write it like that, having rationalized it. And cotangent of 30 degrees, well, that would be adjacent over opposite, right? It's the reciprocal of tangent. So rad 3 over 1, which is, of course, just rad 3. All right, well, what about other angles, like the 60 degrees? We could say, what's sine of 60 degrees? What's cosine of 60 degrees? What's tangent of 60 degrees? Let's just go for those 3. So now we're putting our attention on the 60-degree angle. So opposite is rad 3, hypotenuse is 2, sine of 60, that's rad 3 over 2. Opposite over hypotenuse. Cosine of 60 degrees, adjacent over hypotenuse, so that would be 1/2. And tangent of 60 degrees, opposite over adjacent, so rad 3 over 1, which is rad 3. All right, let's do 3 more. How about sine of 45 degrees? Cosine of 45 degrees? and tangent of 45 degrees. Ah, well, we're going to need the other triangle for that, aren't we? So, all right, I encourage you to learn how to draw that one. Again, it just takes really a few seconds to learn it. So there's the 45, 45. So this is a 1, 1, root 2 triangle. And now we can read our trig function values. Now you can choose any of the 45s on here to work with. I'll just choose this one. So sine of 45 degrees, opposite over hypotenuse. So that's 1 over rad 2. But again, we should rationalize that guy. And that gives us rad 2 over 2. Okay, cosine of 45 degrees is actually exactly the same thing. We get adjacent over hypotenuse, which is 1 over rad 2, which rationalizes to rad 2 over 2. And finally, tangent of 45 degrees. This one's super nice. Opposite over adjacent, so 1 over 1, which is 1. Okay, and again, please don't deny yourself that process of working these out by reading them off a triangle that you drew yourself. Okay, the objective here is for you to be able to produce this knowledge without looking anything up, drawing the triangle and then using SOHCAHTOA to pull off these ratios from the angles.